So for a square matrix, if rank of A is equal to n, we call that matrix a full rank matrix. Now for an n by m matrix A, a matrix that has n rows and m columns, the rank of A is the maximum number of linearly independent rows or the maximum number of linearly independent columns. These two numbers have to be equal. Okay, so that is going to be equal to the dimension of columns of A or dimension of rows of A. So and we already mentioned that this rank has to be equal to the minimum of m and n. If your let's say like if your matrix A has 2 rows and 3 columns, rank of A is definitely smaller than equal to, right? It can't be 3 because you only have 2 rows, so you have maximum 2 independent rows. If n, which is the number of rows, is equal to rank of A, we call A a full row rank matrix. A has full row rank. If the rank of A is equal to the number of columns, which is m in this case, A has full column rank. Okay, so this is like where you have n rows, m columns. If the rank of A is equal to the number of rows, we call it full row rank. If rank of A is equal to the number of columns, we call it full column rank. And if for a square matrix, if A has n rows and n columns, if rank of A is equal to n, we call that matrix a full rank matrix. A has full rank. So let's see how we can determine if a matrix equation has solution or how many solution it has. So for this matrix equation, which let's say has m equations and n unknowns, so it means that A is going to be a matrix with m rows and n columns. X has n elements and B also has m elements. So this is m by n, this is n by 1, so this would be m by 1, right? If rank of A is equal to the augmented matrix rank, if rank of A is equal to the rank of the augmented matrix A and B, if you put B right beside A and find the rank of AB, then we know that this this equation has at least one solution, right? What this means that like you definitely can express vector B as a linear combination of vectors of A. So in this case, we know that definitely our equation has at least one solution. Let's call this number R. So if R is equal to rank of A, if condition 1 is satisfied, and if R is equal to the number of unknowns, then our solution has our equation has unique solution. So for our equation to have a unique solution, rank of A and rank of the augmented matrix AB, if they're equal to the number of unknowns, which is the size of this vector, then we have unique solution. If condition 1 is satisfied, But condition 2, which is r equal to n, is not satisfied. If r is less than n, then that means that there are infinite number of solutions, right? So if rank of A is smaller than the number of unknowns, it means that you can make B, you can express B as a linear combination of vectors of A in infinite number of ways. So if R is less than n, that means that your equation has infinite number of solutions. Okay, and if this condition is not satisfied, then it means that our equation doesn't have any solution. So we covered all three cases. If rank of A is not equal to rank of the augmented matrix AB, then we have no solution. If rank of A is equal to rank of AB and rank of A is equal to n, then it means that we have unique solution. If rank of A is equal to rank of AB, but this number is smaller than the number of unknowns, it means that we have infinite number of solutions. Let's look at a special case where we call this a homogeneous case, where the right hand side is a vector of a vector of 0. B is equal to 0. In this case, if rank of A and rank of AB, these two are always equal. Why? Because this doesn't add any more information here. You remember that if we have a vector of 0, like we can express this as linear combination of the other rows or the other columns. So this, in this case, is a column, so we can express this as a linear combination of the other columns inside A. So rank of A and rank of AB are always equal. Does this set always has a trivial solution x equal to 0? So for sure, there is always a solution here where like all the elements of x is going to be equal to 0. If you want to see if this equation has a non-zero solution, a non-zero solution can happen in which at least one unknown is 0, exists if only rank of A is less than n. Okay, rank of A is less than n. If m is less than n, the homogeneous set always has a only has a non-zero solution. Okay, so this is an m by n matrix. This is an m by n matrix, and this has n by 1 elements. So the size of x is n by 1. If rank of A is smaller than n, then we have at least one non-zero solution, because like we already know that we have a solution which is x equal to 0. We want to see if we have other solutions, right? If we want to have other solutions, it means that rank of A has to be smaller than the number of unknowns. We want to have like more than one solution. So in that case, this is the condition. Okay. Otherwise, if rank of A is equal to n, it means that we always have only the 0 solution for this equation. So let's look at this example. We have 3 equations, 3 unknowns. So we made the matrix of coefficients, we made the vector of right hand side. Let's actually, like, this is solving the system of equation using the method which is finding inverse of A multiplying it by B. and the second method shows how to solve it using the fsolve function. First, let's see if we can determine if this system of equation has any solution or how many solutions it has. So let me write down the coefficients, and then we go to the MATLAB to see if we can determine how many solutions we have. So let's switch to MATLAB. Okay, so like this is our A. A is equal to 400, 1200, 800, 110, 570, 340, 90, 360. Let's just like do this. So this is A. B is equal to 8800, 3380, and 1020. Okay, so first of all, if you want to find out if this matrix is invertible or not, you can just find the determinant of A. So this was what was shown in the previous slide. So this is a very small number, right? It's a very small number. It can be like a numerical error here, so it can be interpreted as 0. So let's see what rank of A is. It's 2. So this matrix is not full rank, right? So this number is actually 0. This is basically like MATLAB, it's like showing it like very precisely. It's not showing it as 0. But it is 0, so you have to be very cautious when you use like any software package. If you find the rank of A, this is basically showing that this matrix is singular. So if it's singular, its determinant has to be equal to 0. Let's now look at the rank of the augmented matrix A and B. If I put B beside A, and let's look at this one. It's also equal to 2. So that basically shows that rank of A and rank of AB are equal. So this means that we can definitely make this vector out of linear combination of these 3 vectors here. Okay, so rank of A is smaller than n, which is 3. And rank of AB is equal to rank of A. So can you tell me how many solutions does this system have? How many solutions do we have for the matrix equation AX equal to B? We would have infinite number of solutions, right? It's not going to be unique because this is not a full rank matrix. But rank of A is equal to rank of AB, so we can make the vector of right hand side from the vectors inside A, so that shows that we would have infinite number of solutions. So this is how you can determine if how many solutions a matrix equation has. These are showing other examples. So here we are again looking at a matrix equation. This is the matrix of coefficients. This is the right hand side vector. We are finding the solution using the Gaussian elimination. Okay, let's actually do this in MATLAB so that like this makes sense. We'll see like how this works. So here this is matrix A, this is vector B. We found the solution for this matrix equation AX equal to B, and this is the solution. But however, we wanted to know if this is very exact. But so if this is the solution, then it means that AX has to be equal to B. So we wanted to calculate B minus AX and to see if we get vector of zeros. We didn't get exactly 0. We got something very small. So this is called round-off errors, right? You always remember that these packages that we use, they are numerical packages. They use optimization, numerical methods, and in order to solve the equation, we always have round-off errors. So it's showing this as minus 1, 1, and 0, but we just like if you subtract B and AX, if you subtract AX from B or B from AX, you will see that this is not exactly 0. We call this a round-off error. Okay, now let's look at rank of A. It's 3, so it's full rank. Rank of A, B, is it capital or yeah, B? It's 3. So rank of A is equal to rank of AB, and it's equal to the number of unknowns. So this shows that this solution that we found is unique. This system, AX equal to B, has only this solution. Let's look at another example. So here we have 3 equations but 2 unknowns. This is a 3 by 2 matrix, but B is still 3 by 1, and X has only 2 elements, so we only have 2 unknowns, right? And we used the Gaussian elimination, and the Gaussian elimination method gave us this answer. This is the round-off error, so it shows that this answer, if it's not going to give us exactly what, if I multiply A by this vector, I'm not going to get exactly the vector B, which is, I'm going to show you. So like let's do this. A multiplied by X, it's going to be this one. B is going to be this one. So we didn't get exactly what we wanted to get. So why did this method give us a solution? Let's see what rank of A is. It's 2. Of course, we have 2 rows and 3 columns. Oh, sorry, we have I'm sorry. We have 3 rows and 2 columns. I made a mistake. This has 3 rows and 2 columns. We have 2 unknowns, and B is 3 by 1. But rank of A had to be smaller than equal to 2. It's equal to 2. Let's look at rank of A, B. It's 3. These two are not equal. What does this tell us? This tells us that this system has no solution. AX equal to B has no solution. There is no X that you can put here that makes R equal to 0. So what what A backslash B gave us, it's not a exact solution of this method. That's why I mentioned that when you use tools, you have to be careful. You have to know what you're doing. So in this case, if like we call this system an overdetermined system, it means that we have 3 rows, 2 columns. We have 3 equations and 2 unknowns, right? We have more equations than the number of unknowns that we have. In most cases, one of this equation is going to be inconsistent with the other equations. So we have too much information. We have too much information, then we have more information than we need, right? Most of the time, one of these equations is going to create inconsistency. So for a system that is overdetermined, the left division method, it's not going to give us the exact solution, but it's going to give us the least square solution. It means that it gives us the solution that makes R, which is the error, minimal. In what sense? In the least square solution. It means that if you find the let me show you R here. So this was R, right? So it means that the solution that we got here, it would minimize R in the sense of least square solution. It means that if you raise this to power 2, raise this to power 2, and raise this to power 2 and add them, right, and find the square root of that, this R would have the minimum square roots of these components, right? So then basically this is the solution that provides the least square this is the vector that provides the least square solution. It's not the solution that makes this equal to 0, because this system of equation has no solution. We already saw that rank of A is not equal to rank of AB. Okay, so you have to be very careful when you use this one. So again, I want to emphasize on this that we have 3 rows and 2 columns. We have 3 equations, 2 unknowns. So here you have an overdetermined system. If you have 2 unknowns, ideally we only need 2 equations to find a unique solution. If you have 3 equations, most probably one of these equations is going to be inconsistent with the other 2. So then that means that our system doesn't have any solution. Like I'm going to use an analogy here. So let's say that you want to go to a certain address. Let's say you want to go to Metro Town and you want to ask people, and they're going to give you information, right? What happens if you ask too many people and the information that you get from them is inconsistent? It means that you can't go to Metro Town, right? Right, let's say like one of them tells you that like it's in Burnaby, the other one tells you that, oh, it's gonna be in South Burnaby, the other one tells you that it's in Calgary, right? So then like most probably an overdetermined system, it would have one equation that would be inconsistent with the other equations. This is not always the case though. Like you can have overdetermined system that has solution, right? How can you find this out? By finding rank of A and rank of AB, and if they're equal, it means that you have solution for the system. Let's look at another example here. So here, this is matrix A. We have 2 rows, 3 columns, right? So we have 2 equations, 3 unknowns. And the right hand side, of course, we have 2 rows, 1 column. So here, this system is called underdetermined, because when we have 3 unknowns, ideally we need 3 equations to find all the elements of the unknowns, all the elements of the vector of unknowns, right? But here we only have two equations. Let's look at rank of A. What can rank of A be? It's definitely smaller than equal to, because you only have two rows. It is equal to 2. Let's look at rank of AB. It is equal to 2 as well. So these two are equal, but this number is less than the number of unknowns. 2 is smaller than 3, which is the number of unknowns. Okay? So it means that this system, this underdetermined system, has infinite number of solutions. The backslash method or the left division method, the Gaussian elimination, would give us only one of these solutions, right? There would be infinite number of solutions. This is one of them. Okay, so if the number of unknowns exceeds the number of equations, then the system is called underdetermined. In this case, MATLAB with the left division method or the Gaussian elimination method computes the solution in the least square sense as well, right? So again, like, it tries to minimize the round-off error, the residual vector. This is called also, like, sorry, I should have mentioned that this is called residual vector, right? So this basically shows the difference between B and AX. So always remember that here, if you have a system like this, you shouldn't always trust on this. You shouldn't think that this is going to be our exact solution. You always have to look at rank of A, rank of AB, and just like use your judgment to see if this is an exact solution or this is an approximate solution, right? In this case, this is an approximate solution because this system has no solutions, no exact solution. For this one, this system, we found that it has infinite number of solutions, and this method would give us only one of them, right? The one that has it's a solution in the least square sense, where the residual vector is minimized. Okay. Why do we have round-off errors? Round-off errors can happen in several circumstances, and when you have large computations, if a process performs a large number of computation, round-off errors may build up. So let's say like you have like so many operations, additions, subtractions, multiplication, divisions. Each of them, you're basically truncating some numbers after the floating point, right? So these errors are gonna add up if you have like a large number of computations. Another case is like when you add a large and a small number, right? So let's look at this method. Like if you do this computation in like MATLAB or like other packages, other numerical packages, you might get an error. Let's say like we have 10 to power 10, which is a very huge number, and you want to add it to 0.001, and then you want to subtract again 10 to power 10. Right? We know that we should get 0.001, but if we do it with MATLAB or some other packages, we might get a different number, right? In this case, since the small numbers mantissa is shifted to the right to be the same scale as the large number, digits are lost, right? So like here, like because we want to make sure that we have the same scale for this computation, for this operation, some digits are going to be lost, and then when you subtract the original 10 to power 10 from this, you get a different number from 0.0001. Same thing can happen if you have a very small number. So smearing, this is called smearing, occurs whenever the individual term in a summation are larger than the summation itself. So like here, like let's say like we have x plus 10 to power negative 20. This is a very small number. If you subtract it from x, it has to be 10 to power negative 20. But if x is much larger than this, then MATLAB might give you 0. Like other packages might give you 0, right? Because this compared to x, if it's very small, it's going to be ignored, right? So round-off errors can happen in these situations. So that's why like here we didn't get the vector of 0. We got like something else. So this is one of the reasons. Whenever we solve a system of linear equations numerically, we need to have some idea of how accurate the solution is. So we want to check if ax equal to if ax minus b is actually equal to 0. If it's not equal to 0, we want to know like what value it has. So this vector is called the residual vector. So we want to find out what this vector is. If x is the exact result of the operation, then theoretically this has to be equal to 0, but most of the time, because of the round-off errors or because the system might not have actually an exact solution, this is not going to be a 0 vector. So this summarizes what we just learned. If rank of A is equal to rank of the augmented matrix AB and rank of A is equal to the number of unknowns, we have a unique solution. If rank of A is equal to rank of augmented matrix AB and rank of A is less than the number of unknowns, we have infinite number of solutions. And if rank of A is not equal to the rank of AB, we have no solution. So this is like what you can use to find how many solutions your system has. I'm showing you a MATLAB function which is called reduced row echelon form. You might have seen this in your other courses. So this would be helpful when we have an underdetermined system. We can always express some of the unknowns in an underdetermined set of functions based on the remaining unknowns. And how we can do that, we're going to see that using an example to make this to just like see like if this makes sense. We actually saw that already using one example. Let me go back to one of this system of equations that we already saw. We saw that this is b3 is equal to -2, and we could express b1 in terms of b2, right? And we found that this system has infinite number of solutions. So this is like what it's expressed here. And always express some of the unknowns in an underdetermined set of as functions of the remaining unknowns. You saw that like over there we could express b2 in terms of b3. We can obtain such a form by multiplying the set's equations by suitable factors and adding the results equations to eliminate unknown variables. So this process, it's called reduced row echelon form. We don't want to do it mathematically, use by hand ourselves. We can use the rref function from MATLAB. So let's look at one example. So here, let's look at the first equation, the system of equation. The vector of unknowns is 1, 1, 1, 1, 2, 3, and 1, 3, 4. And the right hand side is 3, 0, negative 2. So how, let me see, I'll see here. So A is equal to 1, 1, 1, 1, 2, 3, 1, 3, 4, and b is equal to 3, 0, -2. Okay, so what does reduced row echelon format helpful for? It's helpful when we do this. Actually, it would have been better if I write this differently, but let's see what the solution the system gives us is. And like it's taking a long time to. Okay, so this is like the reduced row echelon format of the augmented matrix AB, right? So you see that here. You see that here. This originally was matrix A. Originally, this was vector B. But in the reduced row echelon format, this got simplified. Now, our system of equation is converted to another system. Now, this one basically says that x is equal to 5, y is equal to -1, and z is equal to -1, right? So our system has a unique solution. So using rref function, we can find, using the reduced row echelon format, we can find the solutions of our matrix equation. Let's look at another one. This one, unknowns, the coefficients are 1, 2, 1, 1, 1, 2, 2, -1, 2, 4, 0, and 6, 7, 12, and 4. So first of all, is this system overdetermined or underdetermined? How many unknowns do we have? We have 4 unknowns. How many equations we have? We have 3 equations. So this system is underdetermined, right? We have less equations than unknowns, right? So this system is underdetermined. Okay, let's go to MATLAB and see what the reduced echelon format can help us in this case. This is going to be 1, 2, 1, 1, 1, 2, 2, -1, 2, 4, 0, 6. This is A, and B is equal to 7, 12, and 4. Okay, and then let's do our ref A and B. Okay, so this is what we end up with, right? This is what we end up with if we do the reduced row echelon format. So our equations are reduced to this form. So first of all, we have a row of 0, which we can ignore. The second equation tells us that this was x, this was y, this is z, this is w. So this one says that z minus 2w is equal to 5. Z minus 2w is equal to 5. And the other one tells us that x plus 2y plus 3w is equal to 2. Okay, so here, like, you can express some of the unknowns in terms of the others, right? And so you have now 2 equations. You can provide, like, you can just like give random value to any of the x or y's or z or w's and find the other ones. So you have infinite solutions. But like these infinite solutions, they're not just random solutions. Like, they are satisfying these 2 equations. They satisfy this equation, which is x plus 2y plus 3w equal to 2, and this one, which is z minus 2w equal to 5. So whatever number that satisfies both of these equations can be the solution for this system. Let's look at rank of A, which is 2. Rank of AB, it's equal to 2 as well. And 2 is less than the number of unknowns, which is like 4. So here you see that we have infinite number of solutions, and the reduced row echelon form can give us the format of these solutions, right? So like we know that the solutions for this system, it would definitely satisfy these equations, like where z minus 2w is equal to 5 and x plus 2y plus 3w is equal to 2. Okay, this is the same thing that we saw here. We saw, where did we saw this? Sorry. We saw here, right? We saw that like this system has infinite number of solutions, but these are not random numbers. They satisfy these two equations. They satisfy the b3 is always equal to -2, and their b1 and b2 should have this relationship with each other. So this is how you can find out the solution format for a underdetermined system. Let's look at another example. So I think this one has the same coefficient matrix, but our right hand side is different. So let's just go to MATLAB CLC. I'm just gonna change B. I forgot to take a look at them. It's 8, 12, and 4. 8, 12, 4. Okay, let's look at rank of A, and let's look at rank of AB. Okay, these two are not equal. These two are not equal, so this system has no solutions. Let's look at the reduced row echelon format. So what does this one tells us? This one tells us that 0x plus 0w plus 0z plus 0x plus 0y plus 0z plus 0w has to be equal to 1. Is this possible? It is not possible. So the system has no solution, right? So the reduced row echelon format can help us to determine the number of solutions, the format of the solutions, and etc. Okay, so I wanted to show you this one as well. And if you want to like do this manually, like we use the same process that we did for the Gaussian elimination. Using Gaussian elimination, we made the elements below the diagonal equal to 0. In the reduced row echelon format, we made like we make all the elements that are non-diagonal equal to 0. So like we use the diagonal as the pivot elements for making the other elements equal to 0. If you have an underdetermined system, the underdetermined system does not contain enough information to determine all the unknown variables. Usually but not always, because it has fewer equations than unknowns. This is not always the case. We already saw an underdetermined system which had 3 equations and 3 unknowns. The one with b1, b2, b3. That was also underdetermined. It was underdetermined because the rank of A was not full. So an underdetermined system would have infinite number of, it can have infinite number of solutions. Like you might have an underdetermined system that has no solution as well, if those two equations, if the equations that we have are inconsistent. But most of the time you would have infinite number of solutions with one or more of the unknowns dependent on the remaining unknowns. The left division method works for square and non-square matrices in this case. However, if A is not a square, the left division method can give answers that might be misinterpreted. Okay, So the left division method would give us one of the solutions, but we saw that like we have to be careful when we use the left division method. We have to look at the rank of A, rank of AB, and now we can also look at the reduced row echelon format to see if this solution is actually exact, right? We already saw that for a square matrix we can calculate what it's called the inverse of matrix, and for like ax equal to b you can find the solution also if the matrix is invertible. You can find the solution as a inverse multiplied by b. We have another function in MATLAB called pseudo inverse. So for an underdetermined set, we can use the pseudo inverse to find one of the solutions of the system, using the pseudo inverse multiplied b. This, like, we're not going to get into details of like what mathematically the pseudo inverse means, right? But if we have fewer equations than unknowns, it means that our matrix A is not square. So if it's not a square, the inverse is not defined for a non-square matrix, but it is like the pseudo inverse is defined, right? So we can use the pseudo inverse. The pseudo inverse function gives a solution that gives the minimum value of the Euclidean norm. What is Euclidean norm? It's like when you basically, like, this is like the Euclidean norm. The solution that you find for vector x using this method would have the minimum norm, which norm is defined using Euclidean method, Euclidean norm. So and the solution that's provided by this, it's going to be having the minimum Euclidean norm. Let's look at, I know that you might be confused. Let's look at this system that had infinite number of solutions. This is 712.4 CLC. So this was A, this was B. We saw the reduced row echelon format. We saw that this system has many solutions. Rank of A and rank of B are equal, but they're smaller than the number of equations. So we have infinite solutions. Okay, let's look at A backslash B. Okay, so this is one of the solutions of this. This is one of the solutions of this system. Okay, where x is 0, y is equal to 4.75, z is 0, w is minus 2.5. Okay, so like here, like you get a warning that, oh, that this is rank deficient, right? So like this is an underdetermined system, right? Now let's look at the other method. So like if I try to get inverse of A, let's see what happens. I get an error because matrix must be square, right? But I can get P inverse of A, pseudo inverse of A, and multiply it by B. Okay, this is another solution of the same system. We saw that this system has like many solutions, right? It has many solutions. The backslash method would give us one of the solutions using the Gaussian elimination. The pseudo inverse would give us the solution which has the minimum norm. What does that mean? So let's look at, let me like find this one, x1 equal to A backslash B. and x2 equal to pseudo inverse of a multiplied by b. Okay, you can find the Euclidean norm of any vector in MATLAB using the norm function. Let's find norm of x1. So I want to see like what is the square root of 0 plus 4.75 squared plus 2.5 squared. So this is going to be norm of x1. Norm of x2, let's find that one. It's definitely smaller than norm of x1. So this method would give us the solution out of the infinite number of solutions. This would give us the solution that has the smallest norm. What is norm? Norm is a method that we measure vectors, right? Because like if I give you number 5 and 2, you can just basically tell which one is bigger. But if you want to measure, like compare vectors, we need to have a method to do that. So a norm is something that does it, and there are like many different formats for norm. One of them is Euclidean norm, which basically you raise all the elements to power 2 and add them up and take the square root. That's called the Euclidean norm. And using MATLAB norm function, you can calculate that. So pseudo inverse multiplied by b would give us the solution that has the smallest norm among the other solutions, among all the solutions that we have. The left division method or the Gaussian elimination would give us the solution that minimizes the residual vector in the least square sense. Okay, so for an overdetermined system, we saw that like we can use a backslash b. A backslash b would give us the solution, but this solution is not exact. So let's look at this other example that we had. This other example. So like if I replace b with 8, 12, and 4. So that rref, you saw that this system has no equation. We can see it from this row. And if I find rank of A and rank of AB, so that these two are not equal. But still, I can use the left division method. Okay, if it will give me a warning to be careful about this. This is not going to be an exact solution. Why? Because let's calculate r, which is b minus a times, let's call this one x. Let's first call this one x. X is equal to a backslash b. Now let's calculate r equal to b minus a times x. It's not 0. The residual vector is not 0. It's nowhere close to 0 either, right? But the a backslash, the left division method or the Gaussian elimination method would give us the solution that has the smallest error, the smallest residual vector in the least square sense. So the square, if you raise these elements to power 2 and add them up, for this solution that we have, the residual vector is going to be the minimum. Okay, so you have to be careful when you work with overdetermined and underdetermined systems. So we use these tools, but we have to know what we are doing. So you have to be very careful. So I have some examples for you to solve. So like we can just like basically see like so for this overdetermined system, try to find if it has solution, if it has no solution. If it has no solution, can you find the approximate solution? Other examples are given here for you to work on. Another example here, so like try to work on these examples. This one, like I already solved it for you, but let's first do it yourself, and then you can look at the solution. Maybe I should like do this one for you. So like here we have a problem here, and like once you create the matrix of coefficient and vector of unknowns, if you look at the determinant of A, it's very small, right? It's equal to almost 0, right? And if you, but MATLAB still can calculate inverse of A. Okay, you can still calculate inverse of A, but is this result going to be accurate? So I want you to think about that, right? So like, is this result accurate? Can we rely on this, right? So sometimes like when the determinant is very close to 0, like inverse of A is going to be calculated wrongly using MATLAB. So this matrix, like if you find the rank of it, and you might see that this is not a full rank matrix, right? So you have to be very careful like when you use the methods that you have. So like we now like have many tools to check. We have rank of A, rank of AB. We can calculate determinant. We can calculate inverse of A. We can calculate the reduced row echelon format. So by looking at all of this, then you can determine if your system has a solution or doesn't have a solution, or how many solutions it has. Okay. So we already discussed what a norm is. A norm is a real valued function that provides a measure of the size or length of multi-component mathematical entities such as vectors, right? So like I mentioned that like if you have two scalars, like let's say like 5 and 10, we can easily compare them. But if I give you two vectors, we need to have a tool or a function to give us a real value for these, like a scalar value for these vectors, so that we can compare them. So there are different methods to calculate norm. The one that we already mentioned was Euclidean norm, or it's also called 2 norm. Okay, so you can calculate this using MATLAB using norm of x, or you can also say norm x comma 2. Both of them give you the Euclidean norm. Okay, there are other methods to calculate the norm. They're not going to give you the same number, right? So for different problems, maybe different norms can be helpful to use. In this course, we are going to focus on the Euclidean norm. But there are norm 1 or 1 norm, which is the sum of the absolute values of the elements of the vector, and norm infinity, which is the maximum of the absolute value of the elements. Okay, so let me go to MATLAB and show you this. Let's just like look at a random vector like this one. It's not a good example, it's okay. So norm of x, this is it. Norm of x comma 2 should give me the same thing, right? These two are the same. So by default, norm of x would use the Euclidean norm because this is like more applicable. This is more frequently used. But I can say norm of x and 1, which is giving me a different number. So this is the norm of x by this definition. So we have different definitions for norms, right? They don't give us the same answer, right? So this is basically like you find the maximum value of all the elements and you add them up. So this is basically 4.9 plus 2.57. right? And I can also find norm using the infinite norm definition. If I use the INF, it's going to be giving another method. So this is going to give you the maximum absolute value of all the elements. Okay. So most of the time we focus on the Euclidean norm because this basically represents the length of a vector. We've seen that in Cartesian coordinate systems, we saw that this represents the length of a method as we defined it. These two norms can be used in other applications, in other problems. It might be helpful to use like these to compare different vectors. But for us, we want to compare them, we use norm 2 or like Euclidean norm. More practice questions for you. So again, we have a system of equations, three unknowns, t1, t2, t3. You have to find the matrix of coefficient, the right hand side matrix. You can just like provide like a value for m and g. Like you can assume that m is any number like 2 and g is like 10 or 9.8, and then try to calculate, try to find like how many solutions you have, so your solution is unique or not. Another system of equations here. How many unknowns we have? We have v1, I1, I4, I2, and I5, and I3, and V2. So we have V1, V2, and I1, I2, I3, I4, and I5. We have these three equations and these two equations, right? So, and the values for r's are given. Actually, oh, sorry, V1 and V2 are not unknown. They are known. So we know what V1 and V2 are. So here we have 5 equations and 5 unknowns. The currents are unknowns. So we know the value of V1 and V2. So of course, these are our voltage sources. So we know the value of them. So you just like basically have to form the matrix of coefficients, form the right hand side. In this case, just like it's going to be like V1, if you take V1 to the other side and V2 to the other side, you form the like the constant right hand side vector, and then you can just analyze the system of equation. Another one, this is an underdetermined system. We have 2 equations but 3 unknowns. Try to solve them, try to use the left division and the pseudo inverse method to find different solutions and analyze these 2 solutions. Okay, this is a very good example. So we're gonna see more about this in another chapter. Sorry. So here it says use MATLAB to find the coefficient of the quadratic polynomial y is equal ax squared plus bx plus c that passes through the 3 points, right? So it means that these pairs of x and y that you have here, it should satisfy these equation. So one of the equation that you have would be 4 is equal to a times 1 plus b times 1 plus c. That's one equation. The other equation would tell you that 73 is equal to a times 16 plus b times 4 plus c. And you can find the last equation as 120 is equal to a times 25 plus b times 5 plus c. So you have 3 equations, 3 unknowns, and you can solve it to find the values of a, b, and c. Now it's asking you to do the same thing for this cubic polynomial, right? Now what you end up with here, you have 4 unknowns. Your unknowns are a, b, c, and d, but you end up with only 3 equations, right? So you have an underdetermined system. So you have to figure out If your system has a solution, if it has infinite solutions, like find like maybe 2 of the solutions using the left division method and the pseudo inverse method. Okay, so like this is like, again, like here, like first you have to find first you have to find your equations. So you have like only quartets and dimes. You have 24 of them. So if you call this one x, this one y, or let's call this one q, this one d, q plus d is equal to 24. That's one equation, right? And we know that they are worth $4.5. So q times 0.5 plus d times 0.1 is equal to 4.5. So 2 equations, 2 unknowns, you find q and d. Another question here. So I have provided like many questions here. So in this one, I want you to find the system of linear equations based on the problem description yourself, then convert it to matrix format, and then analyze the matrix format. I briefly discussed what an ill-conditioned problem is. An ill-conditioned problem is like problem that we can't find the exact solution. Like let me go back to this good figure that we had in the beginning of the slide. Sorry. Right, so this is an all ill-conditioned problem, right? So is this the solution, or is this the solution, or is this the solution, is this the solution? This problem is ill-conditioned, right? So we can't find the exact solution easily, right? So for these problems you have to be very careful. So in this problem, if you use the matrix left division to show that the solution is x, y, z, and w are all equal to 1, the residual is exactly 0, and all seems well. However, if we change the right hand side to like slightly, right? So this system is okay, it's not ill conditioned, right? But if we change the right hand side like very slightly, right? So like to 32.1, 22.9, 32.9, or 31.1, the solution is now given by this, right? So the solution, like, it's going to change very drastically if you change the right hand side very slightly. System like this is called ill-conditioned, meaning that a small change in the coefficient or a small change either on the right hand side can change the solution drastically, right? So we saw like why that happens if those two lines were very close to each other. If you change them slightly, like the solution would slide to another point. So using MATLAB function rcondition, this one returns a number that if this is close to 0, if that number is close to 0, we know that this matrix is ill-conditioned. But if it's close to 1, we know that it's well-conditioned. So this number that we get using the R condition, we can determine based on that if the matrix is ill-conditioned or not. So let's look at like I'm gonna write these coefficients here now. 10, 7, 8, 7, 7, 5, 6, 5, 8, 6, 10, 9, 7, 5, 9, 10. Let's go back to MATLAB. CLC A is equal to 10, 7, 8, 7, semicolon, 7, 5, 6, 5, semicolon, 8, 6, 10, 9, semicolon, 7, 5, 9, 10. Okay, so this is the matrix that we have. Let's look at the R condition of A. It's very small. It's very close to 0. So this is an ill-conditioned matrix. It means that, like, if you want to solve the system AX equal to B, any small change to like any of the numbers can change the solution drastically, right? Let me change the matrix slightly. Let's just like say like A12 is equal to like 10. Like not 10, like let's say 100. And let's do our condition again. It's still very small. Like I want to try to see like if I can make this one not ill-conditioned. Okay, so this is slightly better. Still like very close to 0, still like ill-conditioned, but getting better. Let me change another one, A3 equal to say like 500. Still very 0. Anyways, let's look at like another matrix that we had. Let's look at this one. Is this? No. Let's look at this one. Is this R condition ill-conditioned? It's not like it's not very close to 0, right? We saw that this doesn't have any solution anyways, but like let me find another one that gives us like a larger number. So there is no cutoff point to say that, oh, if it's bigger than this, it's ill-conditioned. If it's smaller than this, it is ill-conditioned. If it's bigger, it's not. You just like if it's very small, like what we saw, if it's like almost 0, we know that this is very ill-conditioned. Okay, this one is not, well, it's not ill-conditioned. We can't, like, this is like if it's like for our course, like if you get something in the order 10 to power negative 4, you can assume it's ill-conditioned. This one or this one, we can assume it's not ill-conditioned. Okay, and you can do that using the rcond function. So this would summarize like how you can figure out how many solutions you have, right? So you can find rank of A, rank of augmented matrix AB, if they are equal to the number of unknowns, and you can find the solution if it has unique solution or doesn't have unique solution. You can calculate it using the left division method, or you can calculate it using the pseudo inverse. You can use the rref command to find the solutions as well. So this is the flow chart for the solver. So like some of the functions that we saw here, like in this lecture, determinant, inverse, pseudo inverse, rank, reduced row echelon format, rcond, fsolve. Like we don't use this one. This is like for, like we use it mainly for non-linear equations, and unfortunately I don't have the optimization toolbox to show you this. Transpose, so you can use the quote or you can use the transpose function, and norm. So these are the functions in MATLAB that can be helpful for like this basic linear algebra introduction that we saw in this lecture. Some references that I used for this lecture, they're shown here to acknowledge that. And thank you so much. That was it.